Whenever we have the desire to take a look at the qualitative data that we've collected and test whether some specific distribution fit these data well, the most common way that we're going to approach doing this test is through the use of the chi-squared goodness of fit test. So the chi-squared goodness of fit test is a chi-squared test. It follows the general procedure for running chi-squared tests, but the specific null hypothesis that it's testing is the distribution that we're hypothesizing a good fit for these data? Oftentimes, this is going to come through the form of some specific indication of the proportional breakdown from this distribution. So for instance, all categories are equally likely. This category is 3 times more likely than some other category, this type of thing. But in general, this procedure can be extended out to any type of distributional hypothesis. And so when we are confronted with qualitative data and we need to say, do the data follow some specific distribution, the chi-squared test, goodness of fit test, is going to be one approach for doing this. So the chi-squared goodness of fit test is going to provide us a technique for assessing whether some concrete distribution actually describes the observed data based on a frequency distribution or a contingency table. Most often, this is going to be applied directly to a frequency distribution. So what does the test procedure look like? Well, the desire is to test whether some proposed distribution actually fits the data or not. The null hypothesis is that the distribution does fit the data. The alternative is going to be that it does not fit the data. And so most often we're going to express this simply in words. Right? The null hypothesis is that the given distribution fits. The alternative is that it doesn't. We can always express this in terms of the distributional parameters, right? So the proportion of each category, for instance, and the null hypothesis could be captured that way, but often it will be easier just to use the shorthand here. The observed frequency distribution is going to be denoted by O1 up to OK. And the expected values, which can be computed as EI, which is the probability under the null hypothesis of being in each category, which we denote as PI, times by the total number of individuals, right? So these PI are going to be coming out of the null model, whatever we're actually assuming for the null hypothesis. So we calculate all of our expected values, and then we compute the chi-squared test statistic. So that's going to be the sum over all of the possible values observed minus expected squared divided by the expected. Okay. Under the null hypothesis, this is going to follow a chi-squared k minus 1 distribution, where k is, again, the number of categories that we have in our frequency distribution. And from here, we can calculate our p-value. If we observe a value of x as our test statistic here, then the p-value is going to be the probability that that chi-squared test statistic is greater than x, which is 1 minus the CDF of our chi-squared with k minus 1 degrees of freedom. Okay, and so this is the overarching test procedure that we have here. It is the same as any chi-squared procedure, plugging in our specific hypothesis here. So we can take a look at an example of how this might actually apply in practice. So we have our candy manufacturer. They're filling packages with 25 candies, 5 different colors. They have red, blue, green, yellow, and orange. In one particular package, an individual observes respectively 8, 6, 5, 3, and 3 candies for the total of their 25. And then we're asked if these data contradict the claim that all colors are produced with equal frequency at alpha equals 0.05. And so we need to work out, well, what is the expected value within each of the different categories, right? And then using whatever we've worked out as the expected value, we can calculate our chi-squared test statistic, okay? And so we can come up with our null hypothesis is that all colors are equally likely, right? So we'll say that all colors are equally probable, for instance. All colors occur equally, however you want to frame that. The alternative is going to be that this is not the case. So some colors occur more frequently. Okay. And so then we need to say, well, under the null hypothesis, if this is true, then how many values do we expect to see for each of our observations here? And so then we're looking at, well, what is EI? And EI is going to be PI times N, right? And then for PI, what we know is that P1 plus P2 plus P3 plus P4 plus P5 has to equal 1. And that's going to tell us that Pi is 1 in 5 for all of the i's. Okay, and so then n here is going to be our 25, which tells us that our expected value is 5 for each observation. Okay, and so then we can actually calculate out our test statistic, right? We take our 8 minus 5 plus 6 minus 5, 5 minus 5, 3 minus 5, and 3 minus 5. We square those, divide by the expected value of 5, add that all up, and then we turn towards our chi-squared distribution to actually turn that into a test statistic, or a p-value, rather. Okay, and so walking through this, right, we want to test whether the equal probability model fits. That's going to be our null hypothesis. Under the null hypothesis, all of our probabilities are equally likely, so that corresponds to a probability of 1 in 5 or 0.2. Thus, the expected value is 5 for each of the colors. So under the null hypothesis, we will have the chi-squared k minus 1, which is a chi-squared 4 distribution. K here is 5, right? There are 5 categories. And so then we get the chi-squared test statistic is going to be the sum, the observed minus the expected over the expected, right, where you're squaring the numerator. So 8 minus 5 squared over 5, 6 minus 5 squared over 5, 5 minus 5 squared over 5, 3 minus 5 squared over 5, and 3 minus 5 squared over 5. We add that all up and we find a value of 3.6. Okay, and so our observed value is 3.6 here. And so then to get our p-value, we have to take 1 minus the CDF at 3.6. That gives us a p-value of 0.46, right? So to find that using R, we use the p chi-squared to represent the CDF of the chi-squared. Degrees of freedom here is 4, right? And we're plugging in the 3.6. And so then we take 1 minus that value. And that's going to give us our p-value of 0.46. Now, because that p-value is sufficiently large, then what we can say is that we're going to fail to reject the null hypothesis, right? So the p-value is larger than alpha. We fail to reject the null hypothesis. Given the observations, there is insufficient evidence to conclude that the colors of the candy are not uniformly distributed. So there is no significant difference between the observations and those that would have been expected if it was actually a uniform distribution, right? So here we fail to reject, and as a result, we act as though the uniform distribution is actually fitting the data here. Okay. You can take a look at a second example here. In this second example, we have a student researcher, and they're studying the inheritance of spot patterns in a particular population of ladybugs. They hypothesize that a particular cross of individuals should result in a 3-to-1 phenotypic ratio, comparing many spotted to few spotted ladybugs. They collect a sample of 150. In their sample, 130 are many spotted, and the remaining 20 are few spotted. So do the data contradict the student's hypothesis at an alpha equals 0.01 level of significance. Okay, and so then once again, we're thinking about here our null hypothesis as being that the proposed model actually fits, right? So then we can say here something like there is a the null hypothesis is that P1 is going to be equal to 3 times P2, for instance. Okay, and then the alternative is that P1 is not equal to 3 times P2, right? Again, you could express this in words, you can express this in the notation of the question. It's really up to whatever's making the most sense there, as long as the communication is clear. That's all that really matters, right? In order to get our test statistic, we need to work out our expectation, right? And so then we have that P1 plus P2 has to be equal to 1, right? And P1 here is going to be 3P2. So 3P2 plus P2 is 1. So then P2 has to be 1 in 4, which means that P1 has to be equal to 3 over 4. Okay. From here, we can work out the expected value is going to be the probability times by our total, which is 150, and we can work out the expected value there. In this case, our chi-squared distribution is going to have k minus 1 degrees of freedom. Here, k is going to be 2, and so we're going to be looking at a chi-squared 1 distribution. Okay, and so then we can work out, well, what is our test statistic? How do we go from here? Okay, so then plugging in all of those values into this, we can work through here, right? We're testing whether the set proportions apply. That's our null hypothesis. So we take P1 as 3P2, so that's going to be 0.75. P2 is going to be 0.25 as we worked out. The expected value of 1 is 0.75 times 150, which is 112.5. Expected value of 2, 0.25 times 150, which is 37.5. Right, so under the null hypothesis, we have a chi-squared 2 minus 1, which is a chi-squared 1 distribution. And so then we get our test statistics. We're going to take the 130 many spotted that have been observed, right? Subtract off the 112.5, that's our expected value. Then we take the 20 minus the 37.5, square that, right? Divide each by their expected value, and that gives us 10.8 repeating as the value of our test statistic here. Okay, so then we want to grab out our p-value in this case. So we take 1 minus f1, again here, chi-squared 1 distribution of 10.8 repeating, and that's going to give us 0.001 approximately, right? If we wanted to get this in R, again, we can use the chi-square function to represent our f of our chi-squared here. The degree of freedom is 1. We plug in our 10.8 repeating here, okay? And that's going to give us our 0.001. And so as a result, we have that the p-value is significantly smaller than alpha, right? We want to test at 0.01. 0.001 is smaller than that. And so we're going to be able to reject the null hypothesis. Based on the observations, there is sufficient evidence to conclude that the hypothesized phenotypic ratio is incorrect. There is a significant difference between the observations and those that would have been expected if the 3-to-1 ratio had actually held, right? And so then in this case, we can say that that 3-to-1 ratio is not supported by the data. It probably doesn't hold. We don't necessarily know what the actual ratio is, but the data suggests that that 3-to-1 is incorrect. Okay. And so the chi-squared goodness of fit test is going to be a chi-squared procedure that's used to test whether some specific distribution actually fits well with an observed frequency distribution. Most commonly, it's going to look like the examples that we had, where you're assuming something about the proportions of the different categories, whether that's relative proportions to each other or equal proportions across the set of them. Right? That's going to be the most common way, but any type of distribution that's going to give you those cell probabilities can be applied here, and it's going to work in functionally the same way. Right? You get your cell probabilities, you find your expected value, you compute your chi-squared test statistic, and that's going to translate into a p-value that you can use to test these hypotheses here, right? And so that's going to be the chi-squared test specifically applied to whether a distribution actually fits well, hence the name goodness of fit, right? And this test procedure, again, is going to be very useful whenever you have these qualitative data and you're trying to understand, is the hypothesized distribution actually an appropriate distribution given what you've observed?